attachment. Hey, we got 1 hour. We don't have time, so I'm going to go straight in. I don't know why some of you haven't come back yet, but I'll go on. Can we go on? Can we go on? Wait. I do the attendance first, yeah. Before I let everybody go. Okay, tell me where I need to click. You turn first.
So, first one.
This one?
Yes. Thanks.
The second Michael. Yeah.
This one?
Yeah, the third Michael.
I'll copy you.
This one?
Yeah, that's done. Thank you.
This one? How come you all don't have you all didn't bring the card
Yeah.
Okay, next lesson confirm must bring card. Confirm to entertain this already.
Yes, sir.
The first one.
First one? Any more? Don't have confirm already, yeah? Okay, confirm. Okay, download this example. Later we're going to go through this. And another thing is, yeah, you all can you all try to open this part, this course learning package. You all have it?
For the learning
You all have this?
Learning guide.
The learning guide. So the learning guide, right, provides you with some example and also the explanation. Like I said, Dr. Madenko have downloaded a lot of the videos which you all can look at. The other way is you all can look at this also. Okay, a lot of the explanation is in this. So I recommend you all to also download this, look through some of the examples. Okay, let's take a look at it now. Okay, 100 over pages. So don't need to look at everything. The calculation part, I think is fine. Don't need to look at it. Okay, what in my opinion will be helpful will be things like this part on calculation. Don't need to worry about it. Okay, it does a lot of things like rotational stiffness, all these things which we are not covering here. Okay, what is important is the software itself. There's an example on how to use the software to make some okay, some of the software part of it, which I will go through. What I will go through. Okay, in previous year, I usually I will usually in this in previous year I will go through the two examples here, the truss and the beam example, and I will go through the plates and the shell example. Okay. And I will go through the plate and the shell example.
Coffee.
Okay. This is the plate and the shell. This is the steel plate and shell. Normally I go through them. Because like I say, because previously is assignment 2 or assignment 3. Assignment 2 is on the beam element, which is your beam and your truss. Then I'll go through the plate and shell for your shell, your your shell, then your plane stress, plane strain, and your solid model. Normally I'll do that. But this year round, they decided to put it together as one assignment 2. So it will be harder for me to do that. I will see on how is the progress of the class. But what I will still do is I will go through the example, these 2 examples, okay? But I might not be able to do the physical assignment with you. Okay, but I will do this example, and there's a reason for that. Because this is what you will be examining on. Okay, your plate and you will have one question on the shell, on the beam and truss. You will have one question on the plate and the shell. Okay, so I will need to cover those during the class itself. Okay. Yeah. I will try as much as I can to go through the assignment 2 during class if that is possible. If you all have prepared for it, then I could do more in my opinion now. Okay. That was that. So I repeat few things. First thing is download this learning guide, okay, and also download this example on the cantilever beam, which I will be going through. The cantilever beam is what I will do today, okay, to give you a feel of how to use the software. And third thing is this part here on the module. So there's a lot of video that was been downloaded. Go to the different module. Okay, today we have finished the direct signal method. So we need to go through the video. Okay, go through at home. Some of the background on abacus. Okay, the direct stiffness method. Go through this at home. Okay.
My professional.
And I want you to also go through during your Chinese New Year. Okay, 2 things you need to do. First thing is to read through the assignment 2 question. Okay, the second thing you need to do is to also watch the video on the truss and the beam. Okay, and I'll come back and I'll do the truss and beam. But I need you all to watch the video. Watch video very easy. You all watch a lot of YouTube video. Alright. My daughter loves this YouTube video. I'm sure you all. Okay, can watch that. So you are supposed to watch out the module 4. Any question? No question. Which one will you all prefer first? Are you all very tired? Yeah. Sorry. No, I have 2 things I need to do before the end of the lesson. First thing is I want you all to read through a little bit of assignment 2. Okay, and I will also run through with you abacus, which I need to do that okay, to let you all mentally be prepared. What is the intensity? Because this is going to be worse than your direct signal matrix. Okay, so which one will you all prefer to do first? Which one will you all prefer? Will you all want to read through the assignment 2 first? Because I want you all to split the group. The reason I want to split you all in the group is because I don't want you all to be lost. I don't want one person do one model, then you all do not know how to do, then you all is stuck there and you waste your time. This is really meant to be very application kind. So I want us to form into how many people we have today? How many? If I want to check attendance, I will not ask you already You also don't know Okay, we have 53 people. Okay, can we split into 6 groups? Okay, let's split into 6 groups. Can we split ourselves into 6 groups? Okay, wait. What's going to happen is we split into 6 groups. Each group can have your own model. Okay, you have your own model, but then everybody will need to do you need to write your own report. Okay, so I suppose I have only 6 different type of model. Everybody will do your own report. Everybody will submit your own assignment. But I want you all to do it in group because, like I said, this is a very application-based type of module. Let's take a look. Okay, never mind. Let's take a look at this. Let's take a look at the assignment 2 first. Can we download? Everybody can go download assignment 2. Let's spend 5 minutes to read through it. Hello. Let's spend 5 minutes to look through this. The reason is because I wanted to go through with you a brief summary so that you all can go back home and read it. Okay, I need to go through with you all briefly. Okay, which will help you in your reading because it's 25 pages. Everybody spend 5 minutes. Read through from page. From page 17, design requirement onwards. Okay? We take 10 minutes to read it. Then I need you all to form into 6 groups, and can I have 1 representative from each group? Write down the list of the names in your member. You write 2 lists, 1 you keep, 1 pass to me, so I can keep track of it. I will look at the name list, so we have the same design. Okay? 6 group. Hey, can you all quickly write down your name and pass to me? As you all read, take 10 minutes. Let's take 10 minutes to 10 minutes to 15 minutes to read through. Then submit. In the meantime, can you submit your name list for each of the group? Actually, I leave it to you all. Yeah, but cannot give me like more than 10.
Less than 10. Minimum less than 10.
Not more than 10. Yeah. Hey, as you all write down the name list, can you read the question? Hey, class, listen to me. There are certain things that you can watch online, certain things that we need to accomplish in class. Okay, so this is one of the things I need you all to form the group so that you all can discuss, because there's no way you're going to YouTube any solution from this. That's why I need you all to form the group. You can be able to brainstorm what is the design you want. You need one more.
你要吃吗？我的uniform ，OK 啦，我们一个名字你可以1/6 of the
Hey, class. 10 more minutes, at 4:50, I'll get somebody to come up to explain based on what they have read, what they understand of this requirement. Okay, I'll get somebody up. Recording is just 10 minutes. Nobody reading, everybody discussing.
No. Engine to be customized and how's your It's a rare one. 这个你说不进啊 ，somewhere here 哈，哦，this one 哈，哦
I just need the name list. Okay, I just need the name list. Write down, keep one for yourself, find a representative.
So this one is the engine that we
write
common shaft.
two lists, one you keep, one you give to me.
Yeah, typical set and an angle range from 42 to 98. 45 and 60 range from 45 and 60 range. Offers several we can read the whole thing. 那我们读完整个。
我不懂啊，我没有在读。Large displacement have higher, better performance. Displacement. This displacement? What's our like small displacement is for like entry level, then large displacement is for higher performance. So the displacement is 这两个的 displacement 好像这个 one engine 的 displacement. Okay, your name now. There's 10 of us in the group. Thank you. And the one circle one is our understanding.
So who is the representative?
Prabhu.
So I can the representative email this list to me. Email the name including the student ID, the name to me. Okay, via the and canvas that email. The name and ID the name and ID. Inside your group then I use this to double check
Multiple teams of so that's why bigger What's the component ID 只是那个 S 那个什么你需要的 email 还是 ID？ 你需要的 ID 还是 email？
So we email your email.
Yep. Thank you.
So may I know what's your email?
Yep. Under RMIT can find right.
I took a picture first day, but a bit blurry.
Yeah. Wait okay, email me from here, right? This.
I try finding people who have this. Alright, thanks.
Oh. 1, 2, 3, 4, 5. Anybody haven't submitted yet?
Yes.
Huh?
Send you by email.
Everybody have a group? Does everybody have a group? Have So there's only 5 groups. So who is not in any group yet? Put a hand. Okay. Anybody else? Huh?
We email you. So we email you. We never write the paper. We email you.
Need to write.
Need to write.
Then later you all Prabhu, there's one Prabhu. Huh? Can the two of you all join them? Is it okay? Is it okay? Can Thank you. Can you two of you join them? Can Okay, class. Listen we got 6 group. Later, right? 5 minutes time we're going to get each group to come and explain. One representative explain what do you understand from this project.
Then do your job.
Anybody ready already? Have you read it? Anybody read it? Hey, I need you all to read it out. Come on. Okay? Thank you. Okay. First,
Shuffle a bit.
who is the first group? If not, I call name. Bravo. What do you? Can you just give a brief intro on what do you think? What is this assignment looking for? Hey, hurry up. Hey, class.
From what I read, is we are doing it based on the connecting rod.
Yep.
And the design space is where we'll be making most of our changes.
Yep. So this
So
is design space.
we'll be using it based on material and shape to improve the overall engine performance and all.
Very good.
Then we need to do for the analysis part. Based on our new changes and everything, then compare it to the old one. Yeah.
Good. Thank you. Your team is what? Trouble team, right? Okay, I'll make a note. If you have a pencil, then we'll Yep.
The website.
Thank you. Okay, next team. Next group. Anyone volunteer? Haris. Haris. From anyone from your group also can. This one is +1, then if never say anything means -1, quickly.
This project is to was to design a quadron. I think there's a customer who wants it. So the modification should improve the performance of the engine in various ways. And also it shouldn't change too much so that the cost, like you need to change the other stuff.
Yep. Continue.
Yes, so, we need to, what's that, compare with the original file, see the performance here.
Okay. Next one. Farah.
We also need to take in consideration all the constraints such as the stress factor and the deflections and the locking up. Then design is based on what's
Okay, so there will be design criteria.
correct.
Okay. Next one. 诗经
Yes.
Maybe we need to consider the act of safety for the metal performance.
Yes.
Vacuum efficiency. Also need to see the fitment. The metal can equal metal or reduce the metal. Give them that performance.
Correct. That means other than design criteria, we also have factor of safety we need to consider. Right? Okay. So you are from which group?
The small paper.
Huh?
The small paper.
Okay. Rajesh, correct?
Yeah.
Okay. Your side. Yeah, that's why important must always be the first one to say.
Yeah, I think just, there's existing
Hey, last.
engine. There's an existing engine, then we modify, based on them, it's we need to modify, then we use a V-twin engine. Is it V-twin engine? Yeah.
Okay, then I let you wait on it some more. Okay, we go to other group first. Shafiq. Huh?
Yeah, definitely. Yeah, 全部
Sorry?
要换
I can't hear you. The fatigue failure. Based on the Yeah, so it's all we are looking more towards the tensile or the compressive load, correct? The main load is the tensile or the compressive load, correct? Okay, are you all done? 剩下你们了。That must be the first one next time. 快点 add something different that nobody said.
Different type of material. What type?
Different material said some already. Huh?
Has to be strong enough.
Just now we said design factor, then design criteria, safety factor.
improve efficiency, reduce weight, stress,
So much cost
geometry.
Huh? I said before. First one to say next time. What else, class? What else is missing?
Must design to existing frame.
Existing frame is what?
That means their whole design, you just design the engine to fit into the current frame and model and everything. Can be used on the existing motor 就对了。
Okay. So you must wait, class, listen. This is very important. So you must make sure that your whatever you are going to
changes.
change, you're going to optimize the dimension, but you must also make sure that
Can be fit into the.
yeah, it must be able to because it's connecting rod, so it must be able to have that preserve the same connecting rod that length, correct? It cannot be too long because the engine will be too big, too small, then you'll be a lot of loads. Okay, the load will be high. So things like this gotta take into consideration. I summarize. I will add on as we go, I try to summarize into a PowerPoint, and I will add as we go along.
Sir, will you be sending us this?
No. This is a brief. Like I said, this is what I'm trying to do here is I want you all to read it because you will see that this is very open-ended. Okay, I want you all to read it, and I wanted to do a very quick brief of this so that when you go back home, you can read it more. Then you can think of what else we are considering. I'm trying to highlight is the main point here. Okay, do you get what I mean? Okay, so this is the con rod. So we know that this is the connecting rod. What you will have at the end of the day is something like this. Last time my client always like colorful pictures. Better than colorful pictures, in time you will see is colorful videos. Okay? Doesn't matter right or wrong, they just like to see colorful pictures. Okay, but it's not our job. I mean for somebody experienced, of course, and I will stress it many times to you, to prove the colorful pictures make sense, that is important. Okay? You are not just for the colorful pictures, how to prove it. So this is the engine, there's various components. We're looking at this connecting rod here. Alright? So if you look into the mechanics of this connecting rod, right? Okay, so as the piston move in, okay, I'm not an engine person. Some of you will definitely explain better than me. Okay, but this is my way of trying to explain it. As the fluid comes in, right, as fuel comes in, the connecting rod will move downwards. Compress it, it will go up. Okay, so you go to a cycle. Okay, going downwards followed by going up. Okay, as it compresses the fuel for explosion, once it explodes, okay, the rod will come back down again. Then it will turn this axial to go back for the exhaust. Okay, so you see that most of the time it's moving up and down. Okay, because this thing turns, but the load that transfers through it most of the time is what? Axial load. Okay, it could be tension, it could be compression. Based on this cycle, we know that it could be either. Okay, various components within the con rod. Okay, there's a piston pin, the connecting rod, the crank pin, the bearing plate. Where are our focus? The con rod itself. Just now somebody said very clearly. Okay, there's a design space that we're looking at. Makes sense because when it comes to optimizing this, right? When it comes to optimizing this, many a times you will not do a finite element model for the entire system itself. Most of the time you focus on specific things that you're looking at. Later I have a few examples along the way. If I have time, I can show you some of the things that I did previously. Because finite element take a lot of computational power, so you can't do for the entire engine. You can, but then you will not be able to optimize it like that. Most of the time you focus on something very, very specific. Just now somebody said, very good, the design, there is a limit in terms of the design, the dimension, okay? So you must fit this dimension. Okay, the design space that we're looking at is here. So what does it mean? Do I go and model everything? Think about it. You don't answer now. And if you say no, then why? Okay, you know what I'm trying to say. So if you do model everything, of course, I know what you mean. I'm not saying that. I mean, in the con rod itself, are you going to model everything in the con rod, or are you going to just model this like design space itself? Of course, the result I wanted is in this design space. But is it important for me to model this? The pin, the axle? Is it important for me to do all these things? Think about it. Okay? So the analysis is the shank of the con rod is to be defined as the design space. Primary region for the design modification is the shape. So what we're doing here is this shape here. If you look at it, right, they have deliberately have a groove here. Okay? If they build it over, what's the difference if they was fill this up? And if they have a groove, what is the difference? Okay? Of course, if I have a groove here, that means I'm trying to optimize the material. Right? It will be lighter, of course cheaper. But why do I do it in a certain way? So that was the design that we're trying to look after here. So at the end of this, you will know exactly what we're going to do. What is the design? Or your job is to analyze why I do like a curve. You know, when people do a roof, why is it in the curve? Why do I deduct? Why do I reduce some of the material? Okay. I realize that everybody, when you all get stressed, then you all suddenly get very quiet. Okay. That means you all are getting very stressed with it. We're at the beginning, like I said, do not be stressed at this. That's why I want to be a group. You all can discuss. I want to bring you through the whole thing so you have a better impression of what's going on. So when you read, you won't get lost at all. So the objective, improve the overall performance. So what do I mean? Okay, you can look at different material, the cost. So just as somebody said, we will try out. Let's come back again. You have different material, correct? You can see that the different material, you will use this. This one I will post, then you can use it as reference. Okay, the different stiffness, EA over L. So we go back to the same thing again. These are stiffness, you have different stiffness. Okay, the U strength is different, the tensile strength is different, weight is different, then from there the cost is different. Cost per kg. Okay, cost per kg. That's why the weight will come in also. Okay. The main, in my opinion, right, you can argue, feel free to argue, you want it to be light. But as for me, cost will be one of the main things people look at. So whatever volume you come up with in your model, you will find the net volume, multiply, you find the cost, then argue from there. What is cheaper, what is better. Then in terms of the U strength, that's what somebody also say, main thing is to make it come within the design criteria, correct? I must make sure that it stays within the U strength. There's a different type of U strength here. You can see that in the notes, right? There's two ways to look at it. One way, this is the actual. If you have a tensile, if you're using steel or any ductile material or most metallic, okay, they will behave like this. So this is more like not really an elastic. That's more like a border plateau type of curve. Okay, there is different characteristic to this, which I'm explaining a bit. So this, like you say, is a stress strain curve. Okay, when you load it, it will go up. Then you have this border plateau yielding here. Okay, you see that you have a little bit of border plateau, you have a little bit of yielding at initial part already until it's stabilized to give you a yield strength. Okay, so it's yielding. You see at this point, beyond a certain, it doesn't actually take on more load, but the displacement will continue. That means it's going to plastic yielding already. So if you're a designer, do you want that? Of course I don't want that. Okay, imagine you're sitting on steel, a chair with steel legs, right, or aluminum leg, right? Imagine you load halfway up to a certain point, it suddenly give way. Do you want that? Of course not. You get me? You rather it stay within this elastic region. Okay? But you notice that there's a loader plateau here before the yield strength. That's why normally people simplify it as the elastic perfectly plastic type of material strength curve. You can. In the non-elastic module, you can fit in this curve, but it's not necessary. During the subsequent lesson, I will explain why most of the time, for a simple analysis, which is what we're focusing here, we always do that. This computationally more expensive. This is much easier. Okay? So this is when we simplify, normally we simplify as an elastic, perfectly plastic, or even just an elastic. I just do it, I don't even need here. When I run my result, I just make sure that it stays within here, then this is not necessary anymore. Right? So this is the material requirement. Load requirement. Look here, there is two. You have the pin here, correct? And you have the roller on top. Okay? We say that this is an axial load. Most of the time it's axial load, correct? So what should my configuration be? Should it be a pin followed by a roller so that it's free to extend? Or it should be a cantilever? What do you think? Think about it. Okay? What is your boundary condition? You all know what is boundary condition, right? I'm sure you all do bending moment diagram, correct? So this is where it comes in. Okay, think about it, whether should it be this or this. Okay, if you look into the question, the loading, just like we say, most of the load is due to either the tensile or the compression, but I remember the question did say that it's more of the compression because of the gas explosion. So it's when the chamber explodes, you push it down. So it's a compressive load. However, because it is cycling, the continuum is cycling, right? So the notes also mentioned that you need to consider some sort of eccentricity, correct? Because it's cycling, certain load will transfer horizontally. It's specified at about 20%. Okay? So do you consider other things? Due to the inertia, that means the rod. What is inertia? Inertia means dynamic load. That means for example, if you all have been to a lot of this sort of testing, right? When I press something, you let's say 100 kilonewton, alright? This material can take 100 kilonewton. That is a slowly increase the load until 100 kilonewton. What about if I load it very quickly, instantaneous load? Will the load capacity be higher or lower? Higher or lower? Higher. Why? Because it's correct. Because there is a dynamic capacity, it could be a dynamic load. So that means that your dynamic load will be different from a static load. If you press it slower, if you go and try yourself with any material, normally when you do it as a dynamic load, there will be dynamic stiffness to it. So it actually rebounds a little bit backwards. So that's why there's a difference. Likewise, when it comes to mass, you also have an inertial load. Okay? Like an inertial load. So because this connecting rod is moving, so that is an inertial load. Do you consider that? Or what about, do you consider, just now we said that this load is due to the explosion come down, right? What about the friction? While it was moving, there will be friction, correct? As it rotates around. Do you consider that frictional load? Think about it, huh? Then the design constraint. Just now somebody mentioned about design constraint. So the allowable stress, he mentioned is what is the stress should have then you also mentioned about safety factor, 4.2 safety factor, correct? So you need to have allowable stress, allowable deflection. Then they also talk about the buckling load. Okay, this buckling load should be quite familiar with it, right? Huh? Yeah, we'll come in later. Like I said, I will add in more. But it's for you all to think about it. So the reason I do this is because I thought that it's important that you all try to frame your thoughts as you all discuss on how your project is going to be. So each of these should be one component. Okay, when you write your report. Okay, then also the.
Will you be uploading this?
This one,
because we also need the materials, right? Because of the people.
It's all inside your PDF. All this inside your PDF. No, that's why I do this like this, is to extract out the information. Yeah, if not, it's very easy to get lost. Of course, I will present it. I can share it. But but the objective is for you all to read it. The objective is for you all to read it. But I want you all to read with a certain focus. Okay. I can share it, yeah. Then after that, right, in the final report, you're supposed to bring in a discussion. Just now, with a lot of things that we talk about. Certain things, you will see that your 25-page brief, right, have a lot of things inside. Not everything we are considering in the final element model. You can bring this up for discussion. Some we talk about friction, inertia, correct? Buckling. Do we consider all of these things? Some of these things, that's why I want to bring up, like for example, your piston speed lah, your rod strength, your rod weight lah, those things. That's not necessary. It need to be brought in the model because make it way too complicated. Chances is the dominant load will be the one I look at. The rest of the things, maybe I don't look at it first. You know? Okay?
But do you care how many words, how many pages?
I really don't care. Yeah. So long as you show me, you understand. If you write a lot of Abaqus is a very good software. Every year I have this comment. You do this, clicking the file model, press save or that type of thing, then confirm you don't understand. Then that will be marked down. If the job is to convince the client that you understand the topic. That is the most important thing. Okay, that was it. I can upload this. Next time we talk again. Next time we will meet again for the next lesson. When you all discuss how you all want to do this. So the main thing is before I forget. Okay, now one of the things that was missing, which I was intending to do but I didn't manage to. Remember we talked about how a model, right, could be simplified, which is also mentioned in the which is also mentioned in the report. Okay. You know when we talk about just now, we always mention this like cantilever rod. I can model as a 3D model, or I can do it as a 2D plate, project the thickness, or I can do it as a 1D rod, project the area, correct? So you can actually simplify it using a beam element, a plate element, or don't simplify at all, doing a solid element. Okay, so there is various. That's why you see that inside the assignment tool, right? They also give you certain different type of inspiration to help you, lah. Okay, for example, if you want to do like a groove kind of thing, right? Then it probably needs to be a solid. It can't be simplified, correct? Then, for example, likewise, if you want to do a cutout, you can do it as maybe as 2 plates. Okay. If you do it as a truss, something like this, like a truss. Okay, you can do it as a beam. Okay. Yeah. Yep. So that was it. I will need to do 2 more things. So next week, right? What is going to happen from this lesson onwards is you all will always meet as a group, sit together as a group, and you all will discuss. So you need to discuss like what is a design. Of course, because of the way that this module is being structured, you do 1 beam model, 1 plate model, 1 solid model. Okay, because that's how you'll be tested. So I need you all to cover this area. If not, you go to exam, you don't know how to do it. Okay? Understand? Okay? So you all will decide how you are going to do the beam model, the plate model, and the solid model. Next, the next lesson we meet, I will go into the beam model first. Okay? So I need another half an hour. Can I bear with me for half an hour more? Can Anybody have any question? So I will go through very quickly on let me see. Okay. So I will go through very quickly on abacus. Can you just bear with me for 30 minutes? Okay, so abacus, right, overview. Yeah, first thing is I need you to understand, like in abacus, right, if you launch your software, you realize that it had different modules, it had different modules. Like this, they have different modules, so you need to complete it on this part. It's like a different module. You need to complete each of this module before you can build up the model, which I explained a bit. Okay, then the units we use. Just now I always stress on units. Okay, and I say that you're free to do it because in any finite element software, most of the time you're unitless one. So it's up to the user. It's more demanding on the user to know what you are doing. Okay, because it's meant to be a very generic software which can do for a lot of things. So it requires is based on the user. Okay, then the platform, the tools. Yeah. Okay, so this is the abacus. So this is one of the projects that I did previously. Is on the wafer, those electronics as assembly lah. So like I say, that this model itself, I think I have an example behind. It's about 400 over 1,000 elements. You can't do for the entire. This is meant for those modules by Huawei. So it's meant to be an assembly, daughter card assembly, whereby you signal transfer from one to the other. And we make the reason we are awarded this project is to simplify it, so you don't need to run on a supercomputer. You can run on one of those server computer rather than a supercomputer. So this run on a 40 CPU rather than 100 CPU, which helps, and it runs within 24 hours. So that was done rather than you have something. This is a numerical model. Most of the time it might not give you useful result. Important has something that makes sense, run in a much shorter time so that you can make design modification. Right? The reason you do finite element for what? You can run it so that you can optimize the design. That's what happens most of the time. Okay? The modules within Abaqus. So you're going to come up with the geometry, draw the geometry, okay? Assign the property. Okay, after you imagine I'm doing a hinge now, I must first draw the geometry. Don't need to take photo, this is very generic and you will promise you will all become expert at the end of it. I just need to make sure that I give you a more structured approach. It's easier for you to don't need to take video, don't need to take photo, you will all become expert. First you need to come up with the geometry. I need to draw the hinge, draw the pin, okay, and then I need to assign a property with this steel, aluminium, then I need to put them together in the assembly module. Place them together, the hinge, okay, the pin need to come into the hole of the hinge, right? And then I'm going to give you a step. Like we said just now, there's different type of analysis, it could be dynamic, it could be static. I need to define the type of analysis I'm doing. And you need to have an interaction, so there will be a contact. Just now we said friction, right? So you can assign an interaction. That means the pin, how does the pin interact with the hole, frictional force. But in this module, because we are doing more of the basic stuff, interaction will not be considered. So we do need to consider the interaction module. So we skip over the interaction module. After that, we have a load, whereby you have your boundary condition, your U1, U2, your F1, F2, is all the load here. Your degree of freedom is all here. Okay, under the load as module. Then you do your mesh. Remember, talk about discretizing into regular, this discretization. After you run your model, and you get your colorful pictures. Okay? So in Abaqus, right, there's two ways you can access this module. One way is from here. This is called the module. This is called this is called the model tree, whereby you see all the you have nearly the exact same thing. So you can just know that there's three ways you can do it. One is from this model tree, which I will keep on repeating that. One is from your module drop down list. One is from the icons below. So it's the same thing. You can either access it from here, or from here for the same function. Okay, the parts. Okay, they say parts, right? I'm going to make a part here. Parts. I can either create a part here, I can create a part here. Okay, or I can create a part here. Up to you. Then we talk about creating the parts, assigning the material, the assembly, the steps. This one I will not go into detail because we are running out of time. I will go through one example with you using the cantilever example that I asked you all to download just now. Okay? And then you can carry out the analysis, Okay, one thing to note, this is the important part, and this is extremely important. I expect everybody to remember it. Okay? Just now I said that the dimension, whether it should be meter or millimeter, this is important when you do your model, but you are free to choose. The important thing is you must know what does it translate. For example, if you're using meter, okay, you must know that your force unit, your force unit must be in Newton. Okay, it's meter, then your force unit must be Newton. If it's millimeter, it's still Newton. It's actually stress. Always in Newton. Force always in Newton. Important thing is the stress. So in millimeter, right? So you know that the stress will be megapascal. Because this is always Newton, the stress will be Pascal. The reason behind it is because you do not need to know it now. The reason behind it is because of your gravity. Okay, your density and gravity. That is what that's killing it. Which is equivalent, which indirectly influence your force. But as a background, right, know is when it's in millimeter, your stress megapascal. Meter, the stress in Pascal. So something that is huge. Let's say for example you are doing a bicycle frame, do it in meter. Let's say for example just now you are doing an electronic plate and do it in millimeter. Okay? So you know your stress output is what? Because when your input, it doesn't matter, Abaqus doesn't require you to put in is 10 millimeter or 10 meter, you don't care. You just put 10. That's it. The problem is your stress come out, your colorful picture come out, what is the result? Is it in megapascal or pascal? It also won't tell you. It just gives you a value. It's your job to know what is it. Just now remember we talked about U stretch strength curve, correct? The U strength. So how do you know whether you hit the U strength of 400 for steel? How do you know? So you must on the background you must know what is the unit. Is it 400 Pascal or 500 megapascal? Okay. Yeah. So there's a lot of all this you will become expert after that. So this is what I'm trying to say is that. How come it doesn't show? Okay, finite element can do a lot of things, like including things like CFD. Okay, like even in the wave action, this is something like CFD, whereby you could have a wave coming over, okay, and the overtop. I just give some example here so people understand. So this is another example that I did previously. This for it's a drilling module. So you can see that this is actually a lot of components inside, a little bit like what we're doing for the connecting rod. Okay, but what they're trying to do here, right, is actually only one thing is when you come to the clamp, how do you, there's a clamp coming in here, how do you make sure that it is watertight, the oil doesn't leak out? So for that, because it's a contact, so you need to be very, very sure that it's always in the micro sense, it's always in contact, so you need to design it to make sure that there is a contact pressure all the time for any scenario. That one you will need software to go and actually make sure. If it's something that whether it break, whether it's stressed or not, maybe you don't need to. You can just over design it. But you come to contact, because a little bit of out of contact, you cause a leakage. So those type of things you probably will need a finite element model to it. But the point is, because I'm only looking at the contact surface at the gasket, right? I don't need to model the whole thing. I just extract one part of it, just like what we're doing here. Conrod, we're just looking at certain one aspect of it. Okay? And so you have a lot of results like this. As I was saying, you see that this all the stress doesn't give you a unit, it's for you to know what is the stress for that. I'm not sure whether it doesn't make sense to you now. Actually, I do this is every time, basically when I require something for you to put in the report, I use it as illustration why to do it certain way. But now I know it doesn't make sense to you all at this point in time. But never mind, yeah. Right. Doesn't right, Okay, so this is a double cut assembly I was telling you about. Whole point is that this is a huge double cut assembly. What we're trying to do to simplify it. This example I like it is because I told you many times for somebody that's not so experienced, in your mind is I don't care, I just make it as accurate as possible. The 3D feature I do as a 3D feature, I don't care. Make it as accurate. Why? Everybody likes to be accurate, right? But if your accuracy required to run for 1 week, the model need to run, let's say they do this sort of thing like 100 CPU help, run it for a week. What's the point? You can't optimize the design. There's no way you can optimize the design if you run for an entire week on 100 CPU. You want something that can give you in 24 hours on a 40 CPU computer so that you can optimize the design. Right. Imagine you're trying to optimize the design for this. At the back of it, your client is chasing you and need to start fabricating this. There's no way you can optimize it. This is not like a research project. You know what I mean? So this project, we do a lot of optimization, like for example, for example this the shield plate, whereby they try to reduce the conduction of the signal, right? Connection of the signal, we use it as a plate model rather than a 3D model. So this is some of the things that we try to reduce in terms of the reduced order for simplicity, yeah. So yeah, other than the picture is the video. So the client has to see this out. This something a lot. Like the stress, you can see here, this is very good for optimization. Actually what happened is because this is all this is 0.2 millimeter. This 0.2 millimeter. You do it, which they do in the lab test. But then if with that, right, you cannot see like how well it behaves, because when you manufacture, there will always be offset. So the signal might not touch. It wouldn't be all the pins that touch well. So from this, you can actually determine what's your maximum tolerance when it comes to your fabrication tolerance. So from here, things like Abaqus, things like the finite element module will allow you to be able to illustrate very well based on the contact stress that you see. So you see the middle pin is the one that have a lot of contact. Okay, anyway. Yeah, so they do have the physical test model against the numerical model. Yeah. It help you to explain like why is the model behaving in a certain way. Okay? And why are you optimizing your design in a certain way? Yep, I think that was all I want to show you. I will do a very quick run through of the model. So just now I say I asked for everybody to download. What is it? Oh yeah, I asked.
Yeah.
I asked you all to download this example, correct? Okay, so I would, because the learning guide doesn't give you the solid model one. I thought that actually I run through this at the beginning. You appreciate that. What is the step you need in creating a model? Actually, it's quite simple. What we're trying to do here, right, is a cantilever beam. One end of it is fixed. Okay, then you have a pressure load on top of it. So okay, so just now we said that different module. Remember, we said that this slide is the most important. I didn't stress it enough, but this slide is the most important slide. This slide is the most important slide. Many a times when you do this sort of model, right, worst thing is you do halfway in your exam, then you suddenly got problem, it doesn't run. It requires you to do one module at a time. So you make sure that everything is done before you can assemble the whole model together. Okay, so it's individual step. All these steps you must finish except for the interaction. Okay? So you will see me now go through individual module for you to see how it ought to be done. So can you open your PDF for this cantilever, just now the one? You all have it? Or you all really bit tired, you all want to go back already? Up to you all. Huh? Should I continue?
Yeah.
Okay, so I want everybody to open up the cantilever that PDF. Do you have it? Huh? No, man. The software will require one yourself. Okay? I just want to bring you through here so that you have a give you a flavor of what does this sort of analysis do. Okay? So first part, what do we do? If you look into that PDF file, right, it's a very step-by-step approach, which I like it because during your exam, it's very hard for you to do the video. Okay, it's very hard for you to watch the video and do your exam. But this way, right, if you do it step-by-step wise, it actually help you to. It actually helps you to, like, for example, you see, creating a part. Okay, you go, what do you say? They say that you go on to this part module, click the part, okay, then quick create part, then what is the dimension? It gives you a step-by-step approach, especially when you're not familiar with it. It helps you, in my opinion. I think this way is faster than you keep on scrolling back and forth in your YouTube. Okay, in my opinion, this is faster. Okay? So I just do it once. Okay, so we are doing a 3D model. Okay, so it will be 3D, deformable, solid, extrusion. What does it mean? It means that I will do, you remember we said this is either a projected, I would say it's a projected one, right? So I'm doing a 2D plate, it's 2D. I'm projecting it to the 5mm because it's 3D plate. Okay, so I draw a 2D plate first. Okay, before I project it. So now I'm doing this. Just now this is negative, right? Okay, I'm drawing this part first, projecting the thickness. Okay, so 600. 600. The grid size is not very important. So you just roughly how big is it? You can exceed it when it doesn't matter. Okay, then you just draw a rectangle. This also doesn't matter. You can draw any way you want it. Because the way Abaqus does it, right, is after that you go in and you specify how you want it exactly. Okay? And what's the depth of the beam, which is 20. Okay, after that you press done.
So does it matter if you use the
Doesn't matter. You get 5mm. Then you have the 3D beam. So this is the first module, part. Create the geometry. You know just how we say this is the geometry. So what we do now is create the geometry and finish the geometry. Okay. Next thing is what? Give it a property. Okay. Go to property. See, it's one by one you drop down. Go to property. The name doesn't matter. You can name it. You will see in your in-depth notes, right? You have a lot of things that name it, what name it. All this name is not important. Okay, the step is important, but the name that you how you name it, the material steel or material one steel, all this, the name is not important. Okay, in our module, we are always doing elastic material. Okay, so it's elastic material. Remember, all these things is familiar. Is what? Your Young modulus, correct? EA over L, so you need to create an E. Okay? Just now when I said, if it's in millimeter, your stress should be what? Very good. Somebody say something, huh? Sorry? Megapascal. So if in millimeter, your stress will be megapascal. Okay? So what's the Young modulus of steel? It's about 200 gigapascal. Okay? So if you are 205 E3. Okay? So this is megapascal. Alright? Poisson ratio about 0.33. Okay, so after you create the material, you need to assign a section for it. The reason you do that is because inside a model, right, it could have more than one type of material. That's why inside each, let's say I have a beam, right? I could have a composite beam that I want to do just now. I could be a composite beam. One side, one material, so that's why it requires you to create a section for that. Okay, what turn green means that it's assigned properly. Okay? Then I go to the next one, assembly. We say what? Assembly is to bring the different parts into a model. In our module, we are doing a very beginner course, so we only have one part. So your assembly only have one part to bring in. Okay? And go to step. In this module, because we are also doing the simple one, is always linear elastic. So we can do static general or we can do linear perturbation. It doesn't matter. I will explain subsequently why we do static general and why is it linear perturbation. But both ways is fine. Okay, after we go to load. So this is a cantilever beam. So one end of it needs to be restrained, correct? hand side. U1, U2, U3. Because this is a 3D beam. Because this is a 3D beam, okay? Imagine this is a 3D beam. I am restraining the individual nodes. Okay, I'm restraining individual nodes, okay? So I only need to restrain the translational degree of freedom. I don't need to do it rotationally. Okay, if it's a beam on its own, a 2D beam element, if it's a beam element, I will need to also restrain the rotation. But in this case, because it's a solid, I only need to do it in the translational. Why? Because imagine this part, right? If the top and bottom is restrained, actually form an equivalent couple. It will be restrained rotationally, it doesn't matter. Correct? Okay, then in the pressure load. You will not be able to appreciate everything now, so it doesn't matter, so don't need to be stressed. So it's just for you, like I say, to give you a flavor of the day. I just need to know what's the load. 0.5. Okay? You see, now I add in the load, right? It also don't need me to give you the. It also never require me to come up with what is the unit for that. Okay, so it's the pressure load is what? Newton per millimeter square. Correct? So it's what? Megapascal. Again, after go to the mesh, select the type of element. So you see, this is very different from a direct stable vector, right? Okay, is it very difficult? Okay, you add in the seed. The seed is what? Is how many discretized? You see now it's 20. Just now this is 25, correct? If it's 20, that means you see that it will have 20, or it's 10. Ask for what? Ask for 10. Okay, so this is I can't remember. It's about 20 or 25. It's about 20 or 25, right? For the length and for the depth. So when you say mesh size of 10, means that I only want each element to be about 10 millimeter each. So it could be, if you put one, then you have a lot of elements. Okay. So of course, like what we do, remember for this one, discretizing each, right? So this is the same thing. The more, the better. Okay. From an accuracy point of view, of course, the more is the better. But from an engineering perspective, as an engineer, the more shows that you're not very experienced. You don't know what you're doing. You get me? Everything you do as a 3D, it tells me that you totally do not know what you're doing. Understand? Okay. If everything, like just now remember what we said, for this type of beam, let's say a regular beam, how many element you need? One element for shear. You get me? It's non-linear. It's purely linear elastic. One element will be more than enough. Agree? A tapering one, maybe 5-6 of them, then you get close to the analytical result. What about bending? Maybe 10, normally 10. Okay, if everything but the regular cylinder, you give me 100 element, it just shows me you don't know what you're doing. I will read your report in more detail. Okay? You look out for sign like this as an engineer, like whether the person experienced or not, based on things like this that they do. Okay, after that we will create a job. Run it. That's it. Pass. Okay? And you get your misses. This type of thing, what is the stress you look for? What is misses stress? What is your primary stress? S11, S22, S33. What is your U1, U2, U3? You know, just remember we talked about this in your direct system matrix. We talked about the stress. Previously, we were only concerned with the spring elongating, so we never differentiate the direction. 3D model, is it more than that? Of course, it's more than that, correct? How do you know whether the person is experienced or not? For this type of model, you will not give a misses stress because it got no value at all. Okay? You will give it as a S11. S11 means the primary stress in the X direction. You give it here. Why? Because it's a cantilever beam. So what do you expect? You expect the top beam to be what? Tension. Bottom beam to be compression. Top beam tension, bottom beam compression. This is nearly a pure bending situation. So you expect the bending stress, the compressive stress and the compressive stress and the tensile stress to be perfectly equal, signifying that this is a pure bending problem. Agree? Things like this you will use to illustrate the accuracy of the result. Okay? So that's why if it misses, it doesn't demonstrate the understanding of this at all. Okay? So all these things we will go into in subsequent lesson. That's all I have everybody. Thank you. So but in fast, you see 10 minutes you can do it. So it takes a lot of practice and you can do it. It's not difficult to use the model. The software.
element stress 我们应该是有2个的。
呀，所以你要问一下，是2个。
Question number 3, right?
Sorry?
For this question,